So now I'll just shift. So this is a basic structure of a MOSFET. This is a basic structure of a MOSFET. It has a body. If it is an NPN transistor, N MOSFET, then the source and drain will be of N and the body will be of P. And if it's a reverse, vice versa, that means then PNP transistor, then the source and drain will be of P and the body will be of N. Body will be of N. So it is a basic structure. So there will be a gate made up of metal or polysilicon. We so generally in some cases we use metal, in some cases we use polysilicon to make that gate. And this gate and the whole body is separated by a small dielectric, that is SiO2. You can change the as per your requirements. You can change that oxide material. You can use SiO2. You can use HFO2. Uh, Nowadays, for negative capacitance NC-FET devices, zirconium oxides and many other materials are used for this oxide. So this is the oxide. So basically, this gate is isolated as respect to current. Basically, with respect to current, this gate is isolated with the body, but there will be capacitance. There will be a capacitance across this junction. So this is an ideal structure. This structure, whatever the structure is here, it is an ideal. In normal course, the gate overlaps both source and drain. In normal course, the gate and this gate is like this. It is overlapped. It slightly overlaps the source and drain region. So when it overlaps the source and drain region, there will also be the capacitance, that is CGS and CGD due to that gate. Due to that gate, there will be CGB due to gate and body. Here will be the capacitance, that is body to source, CSB, and here will be CDB. So there will be 1, 2, 3, 4, 5. 5 such capacitances present inside the device. So this is a basic structure of a device. Again, this I have drawn by myself. So this, if again with the coordinate system, if I'll go, if I'll consider this point as a 0, 0, 0. So this is y-axis and this is x-axis. This is y-axis and this is x-axis. So we as the size, whatever the size given to you, you can draw the structure. For your assignment, the question will be like this. Total length of the device will be 105 nanometers, width will be 30 nanometers, and the source and drain length width will be 30 nanometers. Channel length, this will be a 45 nanometer channel length MOSFET. So the channel length will be 45. Oxide, whatever the oxide we are using, it will be 2 nanometers. Gate metal thickness, that is gate thickness, will be 5 nanometers. So this you have to do as assignment. I will demonstrate with certain different combination. Different combination. So again, what you have to do, we know that since there are two types of voltages, if we go to the structure again, there are two types of voltages. One voltage will be applied through the gate. That will be known as gate to source voltage, VGS. And second voltage will be applied through the drain. So that voltage will be VDS, because we will generally ground the source. Source is grounded. So one voltage will be VDS and second voltage will be VGS. So there will be two current and voltage relationships. One will be between VGS and ID VGS, that is gate voltage with respect to gate voltage and current. And second will be with respect to drain voltage, ID VDS. So you have to plot both. So if I show you, so this is ID VGS. So since we are plotting the curve between, we are varying the VGS voltage. We are increasing in this axis, it is VGS. We are increasing the VGS voltage, and we have to calculate the current for different. So we have to fix the drain to source voltage. So we'll get different curves for different drain to source voltages. For example, if you can see VDS1, VDS2, VDS3, VDS4, VDS5, these all are different drain to source voltages, and we are plotting ID VGS, that is current to VGS. Similarly, this is ID VDS. This is ID VDS, current with respect to VDS for different VGS, for different VGS. So if you know the region of operation below this VGS, this region is cutoff region. This region is cutoff region, and this up to this it is linear region. Current is increasing linearly as we are increasing the voltage. The current is increasing linearly. After this point, if you can see this, though we are increasing the VDS, the volt, if we can see, we are increasing the VDS. The VDS is gradually increasing, but there is hardly any change in the current. But there is hardly any change in the current. So this region is saturation region. This region is saturation region, where the current becomes independent of drain to source voltage, where current becomes independent of drain to source voltages. So there are three regions of operation: cutoff region, in which we consider the current almost equals to zero, that is subthreshold region. Then second region is linear region. You can see this, where current increases linearly with increase in the drain to source voltage. And third region is saturation region, where there is hardly any change in the current with respect to drain to source voltage, that is, it is independent of drain to source voltage. Again, if we go on detail, that is theoretical, you'll get in the theory class. It is not almost saturated. It is not almost like a straight line. It has some slope. It has some slope. That is due to some second order effects that you will study detailed, but that details you'll get in the class. So this is a basics what you have to do in the lab. So what we can do, what we can see, if I'll open the presentation, Alak. So basically we have to see the variation in the current. We have to see the variation in the current with respect to drain to source voltage, with respect to gate to source voltage, and also with respect to temperature. You can see the variation in the current with respect to temperature. For example, if the current is 150 degree, what is the value of current? If he goes on increasing the value of temperature to 300 Kelvin, whether the current is increasing or decreasing, you have to see, and you have to mention why if we are increasing the voltage, or if we are increasing the temperature, if his current is increasing, why it is increasing, and if it is current is decreasing, why it is decreasing. Similarly, drain doping concentration. If you increase or decrease the drain doping, what is the effect on current? Whether it will increase or decrease, that you have to see and write why it is like that. So there are some, if you can see, again I'll open the device. There are several factors which can affect the current. Our main target is to see the current. Main focus is to see the current. That means we want to increase the current, that is on current. We want to increase the on current. For that, what we can change, either we can change the doping concentration, that is, we can change the doping concentration of source, drain, body, that we can do and see whether the current is increasing or decreasing. We can change the length. We can change the length of source and drain as well as channel length to see the effect. What is effect in the current? If we increase the channel length, if we increase the source length, if we increase the drain length, what is the effect in the current? What is the effect in the current? Similarly, we can increase or decrease the oxide thickness. If we can increase or decrease the oxide thickness and see whether the current is increasing or decreasing. If we increase the oxide thickness, what is the effect on the current? So there are so many things which we can change and see the effect on the current. So if I can show you. So these are the this is not related to this device MOSFET. This is some proposed device. This is some proposed device which I drawn, which I have made, and I have figure out how the current varies with the different variations. So what we can vary? We can vary source doping, we can vary channel doping, we can vary drain doping, we can vary gate metal thickness, we can vary channel length, we can vary channel thickness, we can vary source length. These are all the variations which we can do inside our device, And accordingly, we can see the variation in the current. So for example, this is the curves. These are the curves which respect to with different temperature. So if you can see this, when the temperature is 300 Kelvin, when the temperature is 300 Kelvin, the current is highest. We are getting the uh, highest current when the temperature is 300 Kelvin, and the current is lowest when the temperature is less. So from there we can conclude that when we increase the temperature, the current increases. But why it increases, that you have to write. I have written here, but you have to write by yourself. Similarly, if we increase the gate length, there is hardly any change in the current. There is hardly any change in the current. Drain length. This is source length. So you can see this in my device. If I increasing the source length, the current is increasing. The current is increasing. That means the effect of source length, increasing the length of source effect is increasing the current. This is with the oxide. Whatever the oxide I have used, this is with respect to the oxide thickness. Similarly, this is channel concentration. So I am just explaining you how by different variations we have to see what is the effect on the current. So this was the first point I want to explain. The second point, if you can see this, I am in the first graph only. I can show here. I can show you. This is the same graph. This is the same graph, but plotted in the log scale. Plotted in the log scale. So you can see this. This is the. This is the after this. This is the current in the subthreshold current. This is a subthreshold region. This is a sub. We consider this current almost zero. We consider this current almost zero, but this current is never zero. This current is never zero. It has very less value. You can see this variation is from 10 to the power minus 7 to minus 15. That means variation is also very large. With a certain amount, you can see this. If you are increasing the voltage from minus 0.1, from zero point 0.1 to zero point 0.2, current is increasing almost in 10 to the power 2 orders. 10 to the power 2 orders. That is, for 0.1, it is 10 to the power minus 13, and 0.2, it is 10 to the power minus 11. That means 100 times current is increasing, but the value is less than zero and it is almost negligible. That's why we consider this region as cutoff region, but this is, you can see the variation in the current. The variation in the current is very large in this subthreshold region. That means a slight increase in the voltage increases currents 100 times. So this was the basic concept with practicality, how a device behaves. Any doubt?
So this will be part of the assignment 3.
This will be the part of assignment 3. Here I
Like
have
this will
shown
for
you
next after midsem or before midsem only it has to
after
be.
midsem only. After
Okay,
midsem
okay.
only.
Yeah,
This
thank you.
this will be after midsem only, because right now I have just described you how in this experiment I will just describe you how you can vary single value. But in case you want to vary 50 values, if you want to see the variation for 50 different values between some range, so that part I'll demonstrate it in the next class, that is fourth lab, and after that I'll provide you the third assignment.
Yeah.
And anything else? So that means I'll proceed with the lab now. So in the last class, I told you that the basics are same. That means Again, I'll open that PDF image. You need, basics are same, either you create a device or SCM file. For any complex device, the main concept is either you script it or make it and generate the mesh. Once the mesh is generated, you need a CMD file. That means two important files are CMD files and SCM files. Two important files are CMD files and SCM files. So in the last class, I told you, if you have any one SCM file, for example, you have a diode SCM file, you can make any complex SCM file with that. You can make any complex device, you can script it. So I'll show you, if you have a diode or a MOSFET based SCM file, how you can make it to a MOSFET SCM file. Again, CMD file, that you can convert the diode CMD file to a MOSFET SCM file. That is also you can do. Again, that remaining, design.plt and design.tdr file will generated. To see the IV relation, you have to go for the design.plt file. So I'll just go to the tool now. Mm. So So if you can see this, this is a basic SCM file of a diode. This is a basic SCM file of a diode. And with this, I can make a MOSFET. With this SCM file, I can make a MOSFET. So what I'll do, I'll create a folder first, new folder, MOSFET demo 1. I'll copy this first setup file and this SCM file here, copy, paste. Now I'll show you the structure first. So here we have 1, 2, 3, 4, 5, this two contacts, source and drain contact, total 7 regions. We have total 7 regions in our device. 1, 2, this body is third, this SiO2 is fourth, metal contact is fifth, this source and drain contacts are 6 and 7. There are total 7 regions. So we have to define total 7 regions in our device, out of which 1, 2, and 3. 3 regions are of silicon. 3 regions are of silicon. One region is of oxide. One region is of oxide. And rest of the 3 regions are of metal. Rest of the 3 regions are of metal. Again, if you can see this total device, whatever the device I am explaining, it is 0 to 300. That is, its length is 300 nanometers. And what is it? This is 0 and 200. So this, in this axis, it is 200. So it is 300 cross 200. The device is 300 cross 200. So out of which this 300 is divided like that. Source is 100, channel is 100, and drain is 100. length of this length is 100 nanometers, channel length is 100 nanometers, and source length is 100 nanometers, drain length is 100 nanometers. So this width, if you can see this point is 200 and this point is 150. I'll zoom it. This point is 200, this point is 150. That means this length is 50 nanometers. This length is 50 nanometers. This is 100 and this is 50. This is 100 and this is 50. Again, if you can see this point is 200 and this point is 100 and this point is 200. This point is 202. That means the length, this is the length of our oxide is 2 nanometers. The length of this oxide is 2 nanometers. And this whole oxide is all across the channel. This oxide is all across the channel. So the length, this length of oxide will be 100 nanometers. The length of oxide will be 100 nanometers, but its width is 2 nanometer. It width is 2 nanometers. Similarly, the length of this after this oxide is metal. After this oxide, either you can polysilicon or you can use metal. So the length of this metal or polysilicon is 5 nanometers. So this, if it is 200, then this will be 202 because 2 nanometers. And after that 5 nanometers, that means 202 to 205 nanometers. So this will be the metal thickness. So first of all, I have to define 7 regions. So I'll just go to the here you can see only 4 regions, So out of which total 7 regions, out of which 3 regions are of silicon. So what I'll do, I'll copy one more silicon region and that to N side because NPN transistor. So I'll just copy this N. Copy, enter, control V. So now I have 3 silicon region. First of all, I'll define the 3 silicon region. So let us start from 0, 0, 0. Let us start from 0, 0, 0. 0.000, 0.00, and since I told you in the x direction my whole device is 300 nanometers, so 0.300, and here it is y, it is 200 nanometers, 00. So this is my first region. What is this? That is body. This is body. Body is of P, sir. P. Body is of P. So P. Silicon region 1. So if I'll compare it with the figure also. So this first I have defined this big rectangle which is my body. It is 300 nanometers and 200 nanometers. Now second region is source and drain. Then the 2 regions will be source and drain. So if you can see this, source is going from in the x direction first. Source will go from 0 to 100. In the x direction, source will go from 0 to 100. And in the y direction, this point is 200, this point is 200. So it will go from 150, to 200. In the y direction, it will go from 150 to 200. In the x direction, it will go from 100 to 0 to 100. Similarly, if we see drain region, so drain region, this 100, then channel is 100, then drain will go from 200 to 300. In x direction, it will go from 200 to 300. In the y direction, it is same as source. It will be same as source from, because you can see with respect to y direction, these are identical. It will go from 150 to 200. It will go from 150 to 200. So I'll define that 2 regions also. So N region, this will be side 1, that is source. So it will be from 0.000 to 0.100. 0.100. In the y direction, it will be from 0.000 150 to 200. to 200. 0.1502 to 200. Next, this will be also of silicon. This is region 2. Next, the third region will be side 2, that is drain region. It will go from 0.200 to 0.300. to 0. In the y direction it will be identical. In the y direction it will be identical. It will go from copy, paste, copy, paste. Now I have defined my, okay, again I'll open the figure. I have defined my region. This is body, source and drain. Now the fourth region is silicon. The fourth region is silicon, that is SiO2. So if you can see this, it is all across the channel. It is all across the channel. So channel is from 100 to 200. If you can see this in the x direction, channel is from 100 to 200. So in the x direction, SiO2 will spread from 100 to 200. But in the y direction, if you can see, this is the jest, if you can see, it is just above the device because device thickness is 200. So the oxide is put above the device, that is 2 nanometers. So it will be from 200 to 202. In the y direction, it will be from 100 to 200. So I have to define that. I'll just copy this. Enter, Control V. So it will be oxide. It will be oxide. Oxide is in the x direction, it is all across the channel. So channel is from 0.100 to 0.200. And on the y direction, it will be from 200 to 202. 202. 0.200 to 0.202. That is, oh, I went wrong here. It will be from 200 to 200 to 200 to 202. And this is not silicon. This is oxide. This is oxide, and this will be region 4. This will be region 3. This will be region 3. Now, if you can see, I have defined region 1, region 2, region 3, region 4. Now, three contacts are left, that is of metal. That is of metal. So one is drain. Oh, one is drain, then gate, then source. So first I'll define the gate. What I'll do, I'll copy this because this will be copy, enter, enter, Control V. So first is this is oxide. OXIDE. Next is gate. GATE, gate. So gate, again I'll show you. Gate is where my oxide is ending. Where my oxide is ending. So oxide is ending in the y direction. It is ending at 202. 202. If my gate thickness is 10 nanometers, my gate thickness is 10 nanometers. So it will go from 202 to 212. It will go from 202 to 212. And it is all across the channel. It is all across the channel. So the y coordinates will not change. Y coordinates will not, or x coordinates will not change. So it is exactly same. So here it will now it will start where oxide was, and oxide was ending at 202, and it will go to 212. 212. So this is my gate contact. This is my gate contact. This is made up of aluminum, and this is region 5. This is region 5. This is region 5. Now region 6 will be source contact. Region 6 will be source contact. So I'll give the source as SOURCE source, and region 7 will be drain. DRAIN, drain. It will be region 6. It will be region 7. So the basic thing again, if you can see this contacts is, let us assume this total is 100, this total is 100, this total is 100. So I am placing the contacts, this point is exactly half. So if it start from 0, half will be 50. This total is 100, source is 100 nanometers. So contacts is just half. I am putting the contact that is half. So it will start from 0 and it will go to 50. It will go to 50. Similarly, if we see the drain contact, and the thickness is 2 nanometers. Thickness is 2 nanometers. So it will be 200 to 202, 200 to 202. Similarly, drain total contact is 50 nanometers. Total contact is 50 nanometers. So it is ending at 300. It is ending at 300. So 50 nanometers before 300 will be 250. 50 nanometers before 300 will be 250. So it will start from 250 and go to 300. It will start from 0 and it will go to 50. 0 to 50, 250 to 300, and this thickness is 2 nanometers. This thickness is 200, 2 nanometers. That is from 200 to 202. So last will be source. So it will start from 0, 0.000 to 0.100. This will be same. Copy, paste, copy, paste. So this is contact. No, this is 50. This is not 100. This will go from 50. Sorry, 0, 50, 50. Similarly, this will be same. Copy, paste, copy, paste. And this will go from 0.250 to 0.300. So this way I have defined my all 7 regions. In this way I have defined my all 7 regions. That is body, source, drain, oxide, gate contact, source contact, and drain contact. Now defining the contacts are done. Now contact declaration. So in the diode there were only 2 contacts, p contact and p side and n side. But in the MOSFET there will be 3 contacts: gate, source, and drain. Gate, source, and drain. So what I'll do, I'll just copy one more contact, copy, enter, control V. Now my first contact is gate. My first contact is gate. G-A, gate. Second contact is source. S-O-U-R-C-E. Third contact is drain. D-R-A, drain. So I have defined all three contacts. I can change the color 0, 0, 0, 0, 1, 0, 1, 0, 1. So instead of diode, there were two contacts, there are three contacts. Now the placement of contacts is important. The placement of contacts are important. It is just on the top. It is just on the top. So again, since there will be three contacts, I'll just copy this again. Copy, enter, paste. So first is gate. G-A-T, gate. Drain. Again, the most important part, if I open again the, so I want to put contact exactly at the center. This is gate, exactly at the this point. If this point, if I'll see the coordinates of this point, so this is with respect to x, this total 300. This is total 300. So exactly center will be 150. Exactly center will be 150. So in the x direction, the point will be 150 here. In the y direction, it is just this is ending at 212. If you have seen this, and this is ending at 212, 212. So the my y coordinate, it will be 212. In x it is 150, and in y it will be 212. So gate, it will be 0.150, and in the y direction it will be 21212. This is my gate contact. Similarly, if I see the source and drain, it is tricky. If you can see this is my whatever the aluminum I have applied for the gate or source and drain. This is drain and source. This is 50 nanometers. If you can see this is 50 nanometers, and this is also 50 nanometers. So if I want to apply the contact at the center, if I want to apply the contact at the center, so this is 50, this is 50. So half will be 25, half will be 25. So in x direction, the point will be 25. And again, this is 202. So in the y direction, it will be 202. This, because this is thickness is 2 nanometer, 2 nanometer. This is 202. So exactly at the center, that means this is whole contact, this whole aluminum is 50. So center will be 25. Similarly, this point, you can guess, this is 250 to 300, 250 to 300. The center point will be 275. Center point will be 275. And again, 202, y direction 202. So it will be 0.025, 0.275, 0.202, 0.202. This is contact settings are done. Contact settings are done. Now, the next important part is doping. Doping. Now, in the diode, there were only two regions, P region and N region. Here, there are three regions. Here, there are total three regions. That is source, drain and body, source, drain and body. Body is of P and source and drain are of N. So I'll just copy this N, copy, enter, enter. Now doping concentration. So normally in the MOSFET, body is lightly doped. Body is lightly doped. So lightly doped, that means 1 e to the power 17 is nice enough. The most heavily doped is source region. The most heavily doped is source region. So source region, if you can see, source is this region 2. Source is region 2. Source is region 2. So the region 2 is heavily doped. I'll make it 20. Similarly, drain will be moderately doped. So region 3 is drain. I'll make it 90. 90. That means doping is done. Doping is done. Now again, meshing strategies. You have to define a rectangle such that it should cover my whole device. So my whole device, if you can see, in the x direction, it is starting from 0 and it is going to 200. It is starting from 0 and it is going to 300. And in the y direction, it is starting from 0 and it is going to 200. So any point before 0, any point before 0, and any point after 300. Any point before 0 and any point after 300 in the x direction. Any point before 0 in and any point after 200 in y direction. So I'll just take a point 0.050. This is the point before 0 in x direction. Similarly, any point before 0 in y direction. So this will also do 0.020 because this is the point before 0 in the y direction. But for similarity, I'll make it 50. 20 will also do. I'm telling you 20 will also do because it is the point before 0 and any point after 300. So any point after 300 will be 0.350 and 0. In the y direction, it is 212. So any point after that, so 0.250, 220, any point will do. I'll take 2. Any point I can take. Random point which is just greater than 212. So greater than 212, I've taken. Here meshing will be 0.05, 005, 0.005, 0.002, whatever the meshing you want to give, you can give. Similarly, multi-box, again, if we see the multi-box, it is the region near channel. It is the region near channel. So I'll just open the figure. From there, I can show you. So this is my channel. So this is my channel. Channel is from 100 to 200. My channel is from 100 to 200. I want to make a box, grid box near this channel so that I can apply fine meshing in this region. So this point is 100, this point is 200, this point is 100, this point is 200, this compared to x direction. So any point just near 200, that is if I take 95 here and this is 200, if I take 205, 95 and 205. So this will cover my channel in the x direction, 95 to 205. Similarly, y direction, I take a point from, this is 150 to 200. This is 150 to 200. So any point here 145 and 200, I'll take a point 205, 207. Any point about 200. This whole region will get covered. 150 say below 145 and above 200 to above is 205. So I'll take a rectangle, rectangle with these coordinates. So what I'll do, again I'll go to the multi-box. So this point will be 0.095 and this point will be 0.145. Again from 0.095 to 0.20. 0.5 and in y direction 0.207. So this has defined my multi-box. Again, the meshing here it is 0.02, 0.202 and like this, like saving the structure, rest of the things are same. I just save it. I'll just save it. So this way, what I have done, I have converted a diode-based SCM file, to a MOSFET-based SCM file. I have converted a diode-based SCM file to a MOSFET-based SCM file. So if I now, similarly, if I'll show you, this is VD sweep. I'll just open it. VG sweep. So where is that SCM file? So this is the file. This is the file. What I have created, this is exactly the same file. This is exactly the same file. So this is the SCM file. This will work for any sweep. If you want a current relation between drain voltage and current, this SCM file is common. If you want the relation between gate voltage and current, this is common. So the SCM file is common. What will change? The change will be in the CMD file. The change will be in the CMD file. So that I'll show you. That I'll show you now, and I'll run it also. So this is the basic SCM file. This will be same for both. Either you want ID-VD relation or ID-VG relation. The SCM file won't wanna change. It will be same. Only change will be the CMD file. I'll show you. So I'll just open the CMD file. So this, if you can see this, this is VG sweep. That means you are sweeping VG. ID-VG relation, gate voltage and current relation. So if I'll open this, so as I told you in the graph, ID VG relation, this will be for different VD. You have to set the VD voltage constant. You have to set a VD voltage constant, VDS voltage constant. So for each VDS voltage, you will get a different graph. You will get a different graph. So here you can see this. I have made a separate folder when VG sweep, when VD is 0.5, VG sweep, when VD is 0.1, VG sweep when VD is 1. So this will give me three different curves. This will give me three different curves. So I'll just show you the CMD file, what is there in the CMD file. So one thing I have included here, likewise in the capacitor, I have included models.par file. This parameter files is needed if you are using any material files. So here we have used aluminum, silicon, and oxide. So that's why I have included the models.pr file. So whenever this parameter file you have command you have included in your CMD files, then this models.pr file should be present in your working folder. It should be there in your working folder. If it is not in your working folder, then it will give the error. It will give the error. So what is the difference? You can see here. Since there are three voltages now, source, drain, and gate. There are three voltages, source, drain, and gate. So normally what we do, we keep source to 0. We keep source to 0. So what we have done, we have given the source voltage 0. Drain voltage, we have to fix because it is a VG sweep. So we have fixed the gate drain voltage to 1 volt. You can fix it to any value. So for that respective value, you will get the relation between current and drain gate voltage. So here I have fixed it to 1 voltage. Here I have fixed it to 1 voltage. And what I am doing, what is my goal? I want to sweep my gate voltage from 0 and I want to sweep it to 1. So what I am doing, I am initially making my gate voltage 0 and goal voltage, end voltage, I want to make it 1.00. So it will go from uh, continuously, it will increase in small slots, time intervals, and it will reach to 1 so that I'll get a current voltage relationship. So this is the ID-VD sweep, ID-VG sweep for drain voltage. So if I'll show you the ID-VD relations, so all the things will be same, source will be 0. Instead of making drain constant, I will make gate constant. And I will sweep the drain from 0 to 1. So I'll show you that also. T-fed, VD sweep. This is, you can see this, everything is same. Here source is 0, here drain is 0. That means drain voltage I have fixed. I can fix it to 0.50, 0.50, whatever voltage. No, drain voltage I am sweeping from 0 to 1. You can see this. I am here, instead of sweeping the gate voltage, I am sweeping the drain voltage. It is going from 0, 0 and drain voltage 1, going from 0, 0 to 1, and I have fixed the gate voltage to 0.5. I have fixed the gate voltage to 0.5. So this will give me ID VD relations for different gate voltages. For different gate voltages, this you can show, see here. Yes, ID VD is for different. So this VG sweep and VD sweep, save, run. So for a demonstration, I'll just show you one run. G sweep, I'll show you. I'll just make a folder. Oh, new folder. Demo 1, create. What I'll need first, I'll need a CMD file, I'll need a SCM file, I'll need a CMD file, I'll need a SCM file. I'll copy these two. This demo folder is empty. I'll copy it, CMD file and SCM file. This I copied. Now I need a setup file. Without setup file, I can't do anything. I'll just copy this setup file also. Demo 1. I'll paste it here. Now I told you in the CMD file, if you are including this model file, so you need this model files in your working folder. Otherwise, it will throw the error. So I need model files. What I'll do, you can copy it from anywhere, but I'll copy from models. So I need models.pr file, aluminum file, oxide file, and silicon file. I'll just copy this. Copy, add, VGC, demo, paste. Now, whatever I required, I have copied and I have pasted here. Again, now I evoke the tool. So what? Open in terminal, TCSH, source.setup, SD. Now in SD file, open model, file, open model. I need SCM file, open. Once I'll open this, mesh.tdr file will get generated. So mesh.tdr file is generated. Make sure that whatever the context name are there in the SCM file, same context name should be there in the CMD files. Meshing successful. I'll just close it. Now I want to run it. What I'll do? As device dot dd, because my CMD file name is dd underscore des. So dd underscore des as device. Enter. Now it ran. I want to see the result. As usual, I open it. Design.plt file. Open. Now here, most important thing, most of the persons do mistake. We are plotting the IDVG, current versus voltage of gate, So voltage we will give from gate side, but for example IDVD, current versus drain voltage relationship, what we do, we give the voltage from drain terminal as well as we measure the current also from the drain terminal. But in this case, we give the voltage from gate terminal, but we can't measure the current from gate terminal because the current from gate terminal is zero. We will not get any gate current because gate is isolated. The current measured should be from the drain terminal. In both the current cases, you have to measure the current from drain terminal. In one case, give voltage from VD drain, and in this case, we'll give the voltage from gate. So gate outer voltage x-axis, current from drain, total current right y-axis. So this is the IDVD relation. This is the IDVD relation. IDVG relation. This is the IDVG relation for VD equals to 1. For VD equals to 1. For VD equals to 1. So we can plot for different curves also. We can plot for different curves also. I'll show you because I have already run for different values. So for example, if I'll show you, I have run it for 0.5 also. This is when VD is 1. This is IDVG when VD is 1. I can show you for VD equals to 0.5 also. Design.plt, open, gate, outer voltage, x-axis, drain, total current, right? So this is the current. This is the graph when VD is 0.5. This is the graph when VD is 1. Similarly, we can see for VD equals to 0.1 also. For VD equals to 0.1 also. Open, design.plt, open. I opened the wrong file, I think. Design.plt, open. Something is wrong. So in this way, you can plot for different values. You can plot for different values. Similarly, you can show the VD sweep also. You can show the VD sweep also. I have already run for VD sweep. I'll just open it to show the. I need this copy. Paste. Open in terminal. Enter. 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 File. Design.plt. Open. Here it is IDVD relation. So you give voltage also from drain terminal and you will measure the current also from drain terminal. So what is there? Drain, outer voltage, x-axis, drain, total current, right y-axis. So this is the relation. This is the relation IDVD. As I told you, it will not be ideally saturated. It will be like this. This is due to second order effects. So this is the IDVD relations. So you can plot the IDVD relations for different gate voltages, for different gate voltages. Any doubt regarding this?
Hello, hi, good evening, Chetan here.
Good. Yes.
I just want to see the SCM file because I have a question on the uh, source drain modeling. Okay, can you go to the .scm file?
Okay, just 1 minute. Yes.
Yes, okay. Can you tell me this N side position that you are saying? N side. The second one is first one is clear, 300, 200 rectangle. What is this 0 to 150?
0 to 1, this 0 to 150, this is 0 to 100. I'll just tell you. This is my source region.
Yeah,
if
it
you
is
can see
100,
this,
right?
100. So this is 100 now. This is going from 0 to 100, right? In the x direction,
Yes.
this is x direction. It is going from 0 to 100. In the
Yeah,
y
but
direction, if
in
you can see this, it is this point is 200. This point is 200. If its thickness width is 50 nanometers, so it should go from 150 to 200.
correct.
It should go.
I
So that's the case. I'll just open
uh,
that now. So in the x direction, if you can see this, it is going from 0 to 100.
this
And in the y
150
direction,
written now.
150 to 200. This is x coordinate. This is x coordinate. Na? This is starting x coordinate, ending x coordinate. This is y coordinate. Starting y coordinate, ending y coordinate. This refers to x,
Okay.
y, z. So this is starting point of x. This is end point of x. This is like this is x starting point of x. This is end point of x. This is 0. This is 100. This is starting point of y. This is end. This is starting point of y. This is end point of y. The starting point of y
Okay.
is 150. You can see this 150 in the center y coordinate
Yeah.
and
Yeah.
200 at the center. So it is
Okay.
like
Okay.
this.
So thank you for clarifying. So just for once again, for my better understanding. So
Ha
in
ha
the positions that you have written, right? Like
ha.
the first one will have x and y coordinates, and the next one is also having x and y coordinates,
Ha.
correct?
Yes,
It
you
is
can
not x
say.
x and then y coordinates.
It
It
is
is
you
x
can
y
say
and
this.
x y.
Yes, yes. X1, Y1, X2, Y2. You can say it's like this
Yes.
also.
Okay. X1, Y1, X2, Y2. Okay.
Yes. Okay.
Yeah, yeah. I misunderstood it. I thought it is X1, Y1 and X2,
No,
Y2.
no.
So that's why I was not
No
very
problem.
clear
No
on
problem.
understanding
Now you
how it
understand,
is
huh?
being. Yes, now it is very clear to me. Yeah.
Okay, okay, okay. So,
Thank you for clarifying this.
okay, okay, okay. So this is the first. Again, I will open the flow chart. This is the first way I have scripted the SCM file. Now, if you want to create the device, you can create it also. You can create the device also. So for that, I'll just take the same coordinates. I'll take the same coordinates so that it can be, you can relate it. So what I'll do, again, I'll go to the TCAD. I'll create a folder, new folder, MOSFET demo. Great. So right now this is empty. What I'll do, I'll copy the setup file. Copy, paste, paste. So now I have copied it, I have pasted it. Now I can open the tool. Terminal, TCSF, SD. So this is my SDE window. This is my SDE window. So now I want to make the device. So for that, first common commands, that is, I want to just make the GUI mode to 2D. Again, draw. I have to deselect this auto region naming. From draw, I have to start the exact coordinates. So this is the first thing which I have to do. Now, first I will define my body. So body is made up of silicon. So first, and it is rectangular in shape. So what I'll do? It is already selected to silicon. What I'll do? I'll just select rectangle from here, and I will draw an arbitrary rectangle anywhere in my GUI screen. So I'll just draw a rectangle. Now it will ask for the coordinates. So as I told you, I'll start x is 100, 0.0, and it is body is total 300, so I'll make it 300. So this is my x vertex of body. Now my y, again 0.0 to 0.20, 0.20, 0. So this is my whole body. X coordinates X starting from 0.0 going to 300, Y from 0.0 going to 200. Okay. I'll give the name body. I'll give the name body BOD. Okay. I'll choose XY coordinate. I'll choose XY coordinate. Here from here you can select the coordinate. So I'll just select XY coordinate. So this is my body. This is my body. Now for just to make the source and drain, I have to apply the grids here. I have to apply the grids here. So you can see this in the side. There is one option of grid. There is an option of grid. So you just select this grid. Grid width, you can keep it 0.05. 0. You can keep it 0.0. 0.6. Here also you can keep it 0.006. Show. So this grid I have applied, whatever the size I have kept after the grid, 0.006, 0.006. You can keep it accordingly so that the grid should be visible to your device. So if you want to keep it more, you can keep it more. If you want to keep it less, you can keep. Generally, fit it according to your device size. Fit it according to your device size. If I'll make it, for example, if I make it 0.10, 0.10. So apply. So it will look like this. So this totally depends upon you, what type of grid you want to apply. Just close it. Now I have created my body. I have created my body. Now I want to create the source and drain. So what I'll do, here is one option, snip to grid. Here is one option, snip to grid. The shortcut is a small g. Shortcut is small g. I'll just select this, and here I'll just make source region. So now my source region is starting from 0 and it is going to 100. I have exactly selected. If it is not exact, you can make it exact. You can make it exact. So my source is starting in the x direction, starting from 0 and it's going to 100. And if you can see my y coordinate, it will start from 150 and it will go to 200. It will start from 150 and it will go to 200. It will start from 150 somewhere here and it will go to 200. So this is my source. So I'll just give the name source S shortcut. Okay. So you can see this source is done. Similarly, I'll make a drain. Now drain is exact. Drain is exact. Here the coordinates are interchanged. You want to change it, you can change it. If you want to keep it as it is, no problem. Since I move the cursor from down to up to down, that's why it is showing from 200 to 150. 150 to 200. Okay. This is drain. I'll give the name drain. Okay. So this is drain. Now source drain. I have applied. This is my two regions. Now I want to apply the oxide. I want to apply the oxide. So I have to change the material from here. I have to change the material from here. So I will select oxide from here. Oxide. Now again, I'll make a rectangle anywhere just above here because my oxide is all through the channel. My oxide is all through the channel and it is 2 nanometer thick. So I'll just make a rectangle here. It is in the x direction, it is from 100 to 200, and in the y direction, it is from 200 to 202. 200 to 202. So this is my oxide 0.02 to 0.200. It is oxide. I'll just give the name oxide. Okay. So you can see this oxide has been applied to nanometer oxide. Similarly, now my gate is metal. Either I can use metal or I can use aluminum. Either I can use metal or I can use aluminum. So from here you can see, oh, metal or polysilicon, anything I can use. So you can see this here, polysilicon is also available, aluminum is also available. So it depends upon you what you want to use. You can use polysilicon also, you can use aluminum also. I'll just use aluminum. Again, I'll make a rectangle. So it is from 100 to 200. And it in the y direction, it will be from 202 to 212, 202 to 212. This is gate. So this is it. So one thing I am not making here, you can make it as per as that SCM file. There are two aluminum regions here also. There are two aluminum region here also. So here for the simplicity, because I am explaining here, I am not considering that to aluminum layer also. You for your you can create what will be the its length. It will go from 275 to 300 in x direction, and width will in y direction it will go from 200 to 202. Similarly here it will go from 0 to 50, and in the x direction it will go, in the y direction it will go from 200 to 202. So in this way, that seven coordinates you can define. Here I am not defining him, I have just applied the context directly here. So now what next I have to do, I have to apply the context. So here I will go to context set. First context is gate, GATE, gate set. Next context is source, SOURCE, source. Just change the color, 110. That, then drain, DRAIN, drain. Change the color to 101. Now all the three contexts are set. Now I want to apply them. So first, here you have to select the cursor, and here you have to select the edge. Instead of body, you have to select edge. Now select one contact, gate contact, just activate it, place it above gate, and again go to contact, set contact. The gate contact has been set. Similarly, source, activate, put it over source, go to contact, set. Similarly, drain, activate, place, go to contact, set contact. All the three contacts have been set. Now, next is doping. You want to dope. So how many regions you want to dope? 3 regions. This is N, this is N, this is P. So for P and for N, you have to select the material. For P and N, you have to select the material. So for P, we generally dope with boron, and N region we dope with phosphorus. N region we dope with phosphorus. So for doping, we'll go to device, constant profile placement. Region. So region first is body. So I'll make the name here also body. REGION region underscore P, name, copy. So region B body. It is doped with boron and it is lightly doped to 1E, 1E17. Add placement. Placement has been added. Now second region is source. Second region is source. So source, again, I'll change the name to source. S Yes, it should be doped with boron. It should be doped with phosphorus, sorry. So I'll select phosphorus and it should be heavily doped. I'll make it 20. Add placement. Now third region is drain. So I'll select drain. I'll make it D. Similarly D. Phosphorus, but doping should be light. So 90. Add placement. So from here you can see also body, boron, e to the power 17, source, phosphorus e to the power 20, drain, phosphorus e to the power 19. You can see the doping also. Close. Now doping is also done. Now next thing is you want to build the mesh. So in the last class, I told you how to make a mesh for a complete rectangle. Now here I can to show you how you can make the multi-box. That multi-box concept also I will show you. So for that, go to mesh, define referral window. It should be rectangle. So first of all, I'll define the grid for the whole device. So I'll just make it like this. Referral 1. Okay. I go to mesh, refinement placement. Maximum size, I'll give it 0.01. Minimum size, I'll give it 0.005. Y direction. Zero point zero one, 0.005. I have to select referral window 1, create refinement. It will create the refinement. Now again go to mesh, define referral window, select rectangle. Just select across the channel. Just select the rectangle across the channel like this. Again, it will be referral window 2. Okay. Again, go to mesh, refinement placement. Here instead of 1, you select 2 and change it to 0.01. Make it finer. 0.01, 0.005. Make it 0.02, 0.05, 0.02. Just close it. So this way you have made the refinement. Now go to mesh, build mesh. Name you can give any name. For simplicity, I'll give DGT. Build mesh. So this way meshing is done. I'll just close it. File, save model. I'll save this also. Set DGT. Save. Now I can close it. So now you can see this. Initially, there was only one file, that is setup.tcsh file. Now this number of files has been created. The most important, that mesh.tdr file has been generated. Now what next? You want to run the simulation. For running the simulation, you need CMD file. You need CMD files. Also, that model file is there. You need all the model files. So I'll copy that all the files. tguide, MOS file DE. No. From here, I'll copy this aluminum parameter file, CMD file, models.pr file, oxide.pr file, silicon.pr file. This four files and that CMD file. Copy, tcad, just paste them here. So now all the files are here. I can run the simulation. Open in terminal. PCSH. Now simulation is done. Now we can check the result. Enter. Open. Drain. Outer voltage x-axis. Oh, gate. Drain. Total current. Right. I think I go with the drain. Outer voltage x-axis, drain, total current, side wires. So this is the graph. This is the curve, IDVD relation. So in this way, you can create the device also. You can create the device also if you want to create. So this is a simple MOSFET. If you want to create double gate MOSFET, some fancy tunnel PET device, you can create it by yourself. Any doubt?
So whether we use .scm or .sat, our .cmd file would remain the same, isn't it so?
.cmd file is same. .cmd file is same.
Same. Okay.
Same.
Okay. We
For
just need to
creating the
ensure the
yes.
yeah, we just need to ensure in the .cmd the mesh files properly.
First of all, context name should be same in both SCM and CMD files. And while creating the structure, you should give the context name, same context name, whatever there is in the CMD file.
CMD file. Yes.
Also, the mesh file name.
That's what I said.
Building mesh, you should create the whatever the name you are giving to your meshing file, mesh.tdr file. That name should be there in the CMD file because it will take the input of that CMD mesh.tdr file.
Understood. Yes. That's most important.
Yes. So this is what I have demonstrated you. So for you to perform the experiment, the device dimensions will be like this. The length I can change it, but this is a standard 45 nanometer size. So that SCM file and CMD file I'll provide you for that. You have to just change in the SCM file. Whatever the SCM file will be there, it will be for the 300 nanometers, whatever the device I have demonstrated. You have to change it according to this size. CMD file will be same. There will not be any change in the CMD file. And this you can change the temperature also. You can change the voltage. I have told you how to change the voltage VDS. And similarly, doping concentration you can change in this change you have to make in the CMD file. SCM file. These two changes you can have to make in the CMD file. Temperature and VDS variation will be in the CMD file, and the doping variation will be in the SCM file. So this assignment I'll float after the exam, whatever the midsem is there. Any more doubts?
Sir, I have one doubt.
Yes.
Sir, if we create a using the whatever using the HTML file, if we create, so
yes.
.scm will also get created.
If you create the structure, that .scm file will automatically get created.
Okay, the same way how we write using the script.
No, it's not. It will not be the same. It will not be the same. It will be slightly different. I'll just show you. Where is the SCM file which is generated? It is not. It will be like this only, है ना?
Actually, I tried, so I don't see the full details.
For that, I'll come to the next experiment. You can whatever the work you have done, whatever the structure you have created, you can record it also. So there is one option. There is one option of turn on. You have to turn on the editor. When you turn on the general file, when you will turn on, so whatever the SCM commands, it will get copied, and when you turn off the general, that will be saved in the form of JRL file. That will not be the SCM file. That will be JRL file. It will be same like SCM file, but that JRL file is generated with the SD GUI mode, so its notation will be .jrl.
Yeah, I
So
have
that,
actually, I have, while performing, I saw the difference when I created design with a .str.
that
So
HCM file is not that HCM file what we are scripting. For if you want that file to work, that is JRL file. That will I'll show you in the next experiment, because that will be required when you are sweeping multiple variables. You will use the different tool.
okay,
There you will require the JRL file. So I'll show you that in the next experiment.
okay, thank you.
Anything else? So for the assignment 2, if anybody has not submitted yet, I'll just increase the deadline by 3 to 4 more days, a week also. I can include the week this week also. So next week, I think it's 10th or 11th. I'll just say extend the date up to 10th or 11th. So be sure, please submit the assignment before 10th and 11th, because the second assignment is having the most marks. 7 marks are there. So please submit it before. I'll increase the deadline by more 7 days. So we'll just submit it before the 7 days.
So its deadline is 12th, right? 12th of June by default.
Already 12th, na?
Yes.
So I'll increase, if anybody is not able to submit up to 12th, I'll increase it further to 7 next weekend.
Okay.
But try to
Okay,
submit
thank
it by 12th, because your midsems are there, na? So try to submit
yes,
it
sir.
before midsem. Otherwise, if you are not able to submit, I can increase it to 17, because there is duration is there between assignment 2 and assignment 3.
Yes, sir.
Sir, requesting from my side, can you please extend the deadline, because we have tape out ongoing, so I'm not able to close the
I'll
things.
increase na. I told you na. I'll increase it. Hai na?
Okay, sure.
Okay.
It will be helpful. Thank you
also-
so much for understanding.
Yes.
So regarding the display resolution issue, so we are not getting the
Is
full
anybody
resolution.
else is facing that resolution issue? So
Yes, sir. For me also, it was the resolution issue. I was not
So,
able to fit in screen.
anyhow, by this Monday, I'll just try to because in the last semester also the students were facing that problems, so they resolved it by themselves. So I'll if some students are in contact with me, I'll ask them how they resolved it, and I'll just tell you in by Monday, Tuesday, I'll tell you.
Okay, sir.
Okay, so this will end the class now. For the next, I'll meet you after a month, and I'll after that lab I'll post the assignment number 3, and there will be one situated learning assignment that will be after the assignment number 3. So it will be of 5 marks. I have already shared the Excel sheet with you. So it will be around in the August, last week of July, or starting month of August, that situated learning assignment will be there. Okay.
So this
Yes.
lab assignment 3 is about MOSFET, whatever we
that
have
will
just
be regarding
learned
MOSFET.
now. This will
MOSFET only.
okay. This is our third assignment, which is after the exam.
After the exam.
Okay, understood. Thank you so much. Yeah.
Okay.
Also, sir, our
Yes.
lab, first lab has not been graded yet.
Yes, I'll grade it. 90% I have graded. I was on the leave for that last weekend. So now I'll
Okay.
start grading from Monday onwards.
Okay, thank you, sir. Thank you.